through part 1 of Unit 1. And Unit 1 overall is talking about atomic structure and properties. There were also some chemical analysis pieces in there and some calculations, and that's the part that we are going to focus on today. And as we start reviewing for the AP test, you want to think about preparing for an open note exam. So some things that I recommend having would be having a hard copy of an equation sheet and a periodic table. If you need help getting a copy of those, let me know. You can make notes on your equation sheet. So think about what notes would be helpful to jot down. You don't want to write too many things on your equation sheet because then it might become hard to read. So I also recommend making a one-pager for each unit with easy to reference notes. So as we're reviewing topics, think about what things would be useful to have written down as an easy reference for you to look back at. And really these notes should be no more than 1 page per unit. Maybe even a half a page would be good too. Because if you think we have 7 units, if you do 1 page per unit, that's still 7 pages of things to look through, which is still a lot. But it's going to be better than trying to look through your whole textbook, right? So you want to be smart about the open note nature of this and have a good set of notes to look through. So start thinking about this as you start reviewing, and then you can start taking notes and you can revise it and narrow it down and think about what things would really be helpful to have written down. Here's some examples of one-pagers that I just found, online. These aren't from ones in our class, but you can see this one looks like someone made a one-pager on bond types from maybe a regular chemistry class. Here's an example from what looks like an anatomy class. What's really important with these is that you write it out yourself. So the process of writing these is what strengthens your own learning. As you go through and do the work of summarizing the unit, you might find when it comes to the actual test that you don't even need to look back at your notes. Or if you do need to look back at your notes, you'll be able to find what you're looking for really, quickly and easily. And just as a quick confirmation of, oh, yep, that's the thing that's what I thought, cool, check it and move on. So you want to make sure you really are preparing in advance. Open note test does not mean it's going to be easy. And another recommendation is using a mix of images and words is powerful. That's a recommendation that comes out of educational research. So use color, use pictures or diagrams if you can. So we're going to be looking through these 3 topics in Unit 1. We're looking at moles and molar mass, the composition of substances, and the composition of mixtures. So a quick overview of moles. Remember, moles is a unit we use to count atoms. Since atoms are super tiny, it's useful to have this really big number of atoms to think about, is what we call a mole. So this is Avogadro's number, 6.02 times 10 to the 23rd. This number is on your equation sheet, so that's not something that you need to write down or memorize. It's already on your equation sheet. The other thing that's on your equation sheet is this right here, which is moles equals mass divided by molar mass. So if you would find this helpful, you could, write out what this looks like, rearranged to solve for various things. So solving for mass, solving for moles, or solving for molar mass. So if you want to solve for molar mass, it would be, molar mass is grams per mole. So it would be the mass divided by the number of moles. So there's various things you could think, would that be helpful for me to write that down? You could write out an example of a mole calculation if you think that'd be helpful. And if you don't think you need it, then you don't have to include it in your notes. All right, percent composition. So percent by mass is something that I've seen pop up in a lot of different contexts in the AP test in the past. It's something that could show up later on, like in Unit 4 with stoichiometry, or in other various applications. So it is an important concept. And the percent by mass of something is the mass of the part divided by the mass of the whole. And that could be looking at a mixture. Like we did a lab where we tried to figure out the percent copper in a sample of brass, if you remember that, and we used spectrophotometry. So we found the percent by mass of copper in a brass sample. So what we did is we figured out how many grams of copper there was. We used spectrophotometry to do that in this lab. and we divided it by the mass of your brass sample. Multiply that by 100, you get a percent by mass of copper in your brass. Another application of this would be looking at the percent by mass of an element in a compound. So here's some quick practice questions, which you want to pause the video for a moment and try these. Okay, so looking at this quick practice question number 1, which of the following substances has the greatest mass percent of chlorine? So to find the mass percent of chlorine, you would take the, mass of your chlorine divided by your mass of your entire sample. So in this case, your mass of your chlorine, if you look at your periodic table, 35.5. The mass of the entire sample is 35.5 plus 6.94. So this one is going to have a very high mass percent of chlorine, and that's because the chlorine is so much heavier than the lithium is. It turns out, if you do the calculations, this one has the greatest mass percent chlorine. Let's look at one other example down here real quick, SrCl2. I wanted to look at this one because there's a subscript 2 here on your chlorine. So that means that you have to consider the, excuse me, there are 2 chlorines, so you need to add up their masses. So 35 plus 35, and it's 71 grams. And then I believe this is 87. You end up with something like 45%. But there's 2 chlorines, you gotta make sure you take the mass of 2 of them. And this next practice question, this is another variation on this where we're looking at a 10-gram sample. And a 10-gram sample of which of the following would have the greatest number of oxygen atoms. So when you see a question like this, the ones with the greatest number of oxygen atoms would also have the greatest mass of oxygen. And if you're comparing the same sample size, the one with the greatest mass of oxygen is going to have the greatest mass percent of oxygen. So you want to recognize that this is just another way of asking which of these samples would have the greatest mass percent of oxygen. And so if you do the same kind of process like you did over here, you should find that magnesium oxide is the one with the highest mass percent of oxygen. So the next thing we talked about in this unit was empirical formulas. And remember, we had this kind of rhyme or chant or whatever you want to call it. Percent to mass, mass to mole, divide by small, multiply till whole. Here's an example of something that you might want to write down. If you find that helpful, you could add this to your notes. And the typical problem you might see would be something like this. You've got a compound that's 80% carbon by mass and 20% oxygen by mass. What is the chemical formula of this compound? So what you do is you take your percents and you turn those into masses, and then you then turn those values into moles, divide by the smallest number of moles, multiply till whole. Let's look at this example. Let's do this one and test out this kind of process here. So pause the video, try this quick practice question. All right, so now that you've tried it, if you take a look at this practice question, notice how we're not given percents to begin with, we're given masses. So we can skip this first step. We already have mass. Then we're going to do the next step is we're going to convert mass to mole. So I'm going to take my 2.5 grams of phosphorus, and I am going to convert that into moles of phosphorus. So if I look up the molar mass of phosphorus, I find it's 0.0807 moles of phosphorus. And then oxygen, we have 3.2 grams of oxygen atoms. So this is just oxygen atoms. It's not oxygen gas, so it's O, not O2. And the molar mass is 16 grams per mole. So I've got 0.2 moles of oxygen. So I did mass to mole. Now I'm going to divide by small. So I'm going to turn this into a nicer looking ratio, because right now this is a mess. It's a 0.2 to 0.08 ratio. That's a not very easy ratio to look at. So I'm going to divide them both by the smaller number of moles. So what this tells me is that for every 1 mole of phosphorus, I think they end up with like 2.47 moles of oxygen. And now I want to do, so this is not a whole number ratio. This is like 1 to 2.5. I want to multiply this ratio by some number to turn it into a nice whole number ratio. And what we can do is if we multiply both of these by 2, you will end up with a much nicer looking whole number ratio. So I've got 2 moles of phosphorus for every 5 moles of oxygen. So my formula is P2O5. And if you were wondering about this multiply till whole step, when do we multiply till whole or when can we round? A general rule of thumb is that you can round if you are within plus or minus 0.1 of a whole number, meaning that if you have like 2.07, if that's your value you end up with, that's close enough to round it to 2. Or, 1.93, that's close enough to round it to. But if you have 2.45, that is not close enough to round it to. So do not round that one. That's where you want to do the multiply till whole step. Okay, so only round it if you're within, like, let's say 0.1 of a whole number. So other types of analysis that we might see are combustion analysis and then gravimetric analysis of a hydrate, and we'll look at examples of both of these. So in combustion analysis, this is when you have a hydrocarbon with an unknown chemical formula. So you know it's a hydrocarbon, so it contains carbon and hydrogen, and sometimes it might contain something else as well, like oxygen or nitrogen. But what happens with your hydrocarbon is that if you react it in the presence of oxygen, you get a combustion reaction. In a combustion reaction, you always make carbon dioxide and water. And all of the carbon from your hydrocarbon will end up in the carbon dioxide, and all of the hydrogen will end up in the water. So we can look at the amount of carbon dioxide and water that we formed in this reaction. We can figure out how many moles of carbon and hydrogen were in your original sample, and from there we can figure out the mole ratio. And that's what the empirical formula is. It just tells us the mole ratio of elements within your compound. And then this is something we did in class, but we did sample problems in class, but we didn't actually combust something and collect carbon dioxide and water. That was a little too complicated of a setup for us. One thing we actually did do in class, and this was back in September at the beginning of the year, is analysis of a hydrate. So in our class, what we did, if you remember, we had a crucible and we had a copper sulfate hydrate. And a hydrate means a ionic compound that contains a certain amount of waters. And we were trying to figure out how many waters were in our sample. So we started out with our wet sample, that was our hydrate, and then we heated it in order to drive off the water. And we end up with a dry sample. This is called the anhydrous version. So we're heating it to remove water. And from looking at the mass before and after the heating process, we can figure out how much water was in our original sample, and from that determine the chemical formula. So we'll look at examples of both of those. So here's a combustion analysis one. And this is a slightly simpler version of a combustion analysis than we typically see in the free response. This is actually based on an old multiple choice question, and multiple choice questions are actually a good place to look at for the level of math you're going to see on this year's test, because multiple choice questions are designed for you to have to do some calculations, but you should be able to do them without a calculator. And on the 2020 AP exam, they have said that you can use a calculator. I definitely recommend you use your calculator, but the calculations are going to be designed so that they can be done without a calculator, if that makes sense. So you don't have to have a calculator. So the numbers will be a little bit more straightforward on this year's test. All right. So in this problem, we combust a hydrocarbon, and we observe that we make 0.3 moles of carbon dioxide and 0.4 moles of water. And what we're trying to figure out is what is the empirical formula of my hydrocarbon? So what is my carbon to hydrogen ratio? So let's figure out how much carbon and hydrogen we made here. So we made 0.3 moles of CO2 and 0.4 moles of water. And keep in mind that for every 1 molecule of CO2, we have 1 carbon atom. So 0.3 moles of CO2 means we have 0.3 moles of carbon atoms. For water, it's a 2-to-1 ratio. So for every 1 mole of water, we have 2 atoms of hydrogen, or 2 moles of hydrogen. So 0.4 moles of water means we actually have 0.8 moles of hydrogen atoms. And if you take a look at this, this is something we could do without a calculator and kind of see this ratio. Oh, this looks like a 3-to-8 ratio. So it turns out the chemical formula for this hydrocarbon is C3H8. So that's the way of doing that without using a calculator. But we could also go through those steps that we talked about. So we did percent to mass, mass to mole, divide by small. So I'm going to divide both of these by 0.3. You end up with, for every 1 mole of carbon, we have 2.66 moles of hydrogen. And you might look at that and say, hey, that looks like 2 2/3. So if we multiply, so we get to multiply to a whole step, you're going to multiply both these numbers by 3, you'll end up with 3 carbons per every 8 hydrogens, which is what we just set up here. So this gas is propane, and we figured that out by analyzing what is made during its combustion reaction. So now we're going to flip over and look at some of the free response questions. If you are following along in OneNote, these can be found on the page directly below your notes here. And these are free response questions that have been released by the College Board to everyone taking the AP test. And so I think these are recommended ones for us to work through. That's why I chose these ones. So if you haven't tried this yet, I want you to hit pause and give yourself, 10 minutes or so to work through the first half of this 2008 question. All right, so hopefully you have hit pause and you've tried this problem, and now you're back with us. We're going to talk through this first part here. And a couple things we should look at is, one, they use the word gravimetric analysis. The word gravimetric analysis, that means that you are analyzing something by looking at its mass, by weighing it. So that's what gravimetric analysis means, is that you're going to weigh stuff. The other main lab technique we use to analyze an unknown is titration. So your two main techniques are gravimetric analysis, which is weighing, and titration. And titration, you can either do an acid-base titration, or you can do a redox titration. And I believe we did both of those in Unit 4, so that could be something good to look back at your lab book for a refresher of those, and we'll go over this in the Unit 4 review as well. All right, so something to know about gravimetric analysis, which is an important lab technique, is the idea of heating to a constant mass. And what that means, like in this context, is I am heating a hydrate, and I'm trying to get rid of all the water in your sample. But I need a way to determine whether or not I've successfully gotten rid of all the water. So what we do is you don't just heat it once and weigh it and assume that you got rid of all the water. What you do is you heat it, you weigh it, and then you heat it again, and then you weigh it again, and you probably heat it a third time, and then you weigh it again. And you want to keep doing that until you have reached a constant mass, which means that the mass stops decreasing. And that's what we see has happened here. Between the second and third heating, the mass has stopped dropping. That means we have gotten rid of all of the water. So that is the answer to A. How do we know that we have heated it enough? Well, the mass has stopped decreasing. And you might even look at that data and say, wait, the mass actually went up a little bit. Yikes, what's going on there? Well, it only went up by 0.001, and that's within the range of just normal error of your balance, so I wouldn't worry about that. So that seems good. Basically, the mass has just stopped changing. That's how we're going to interpret that number. And then we're going to use this data to do some calculations. So first, we're going to calculate the number of moles of water that have been lost. So I'm going to take my mass of my initial, hydrate plus the container, which was 25.825. That is my, my wet sample. And I'm going to subtract from that the final mass. So we should always use the final mass. You might be wondering, should I use the second heating because that's in the lower number? No, you should always use that final number. That's a rule of thumb. And this is our dry sample. And if you think about sig fig rules, when we do a subtraction, you follow the rule about how many spots to the right of the decimal you can go. So notice how both these numbers go all the way out to 3 spots to the right of the decimal. So my answer is going to do the same thing. So my answer has 4 sig figs in it. And that decrease in mass corresponds to the amount of water that was lost during the heating process. And I want to take that mass and convert it into moles. So when I do that, I end up with 0.1026 moles of water. Again, we have 4 sig figs in this value. And are they going to stick with a 1 point sig fig deduction on this test since it's a shorter test? I don't know. They haven't said that they won't assess on sig figs, so I think there's still potential for them to grade on that. So might as well practice. And this is something you could always add to your notes too. If you want to write down your sig fig rules, maybe write down a few examples of doing sig figs and calculations. That might make you feel more confident on the test day. Okay, so you got your moles of water lost. And then we want to determine the formula. So the formula of a hydrate in general looks like this. We've got a certain amount of magnesium chlorides and a certain amount of water. So we're trying to figure out what is this value of N here. What's the ratio of magnesium chloride to water in this formula? So we already know the moles of water. So our next step is find the moles of magnesium chloride. So I'm going to take my dry sample, which this is my pure, magnesium chloride plus the container. So this is dry magnesium chloride sitting in your container. Subtract from that the mass of your empty container. And that's going to give us the mass of your magnesium chloride, which is 1.630. Don't forget that final 0 here, because this number should have 4 sig figs in it. So you got to include that 0 there. And then I want to convert that into moles. So I want to use the molar mass here. And then that's 0.01712. And again, this number has 4 sig figs in it. Remember, leading zeros are not significant. And then I want to find a mole ratio. So here's where we can think back to our empirical formula steps. Remember, do percent to mass, mass to mole, divide by small. So to get a nicer looking ratio, I'm going to divide both of these by the smaller number of moles. And when I do, I find that the ratios for every 1 magnesium chloride, I have 6 waters. You end up with like 5.99. That's close enough to round it up to 6. So that is the chemical formula of my hydrate. And for hydrates, you should never need the multiply till whole step. In the case of hydrates, it's always going to be a 1 to something ratio. That's just the way the kind of structure works there. All right. And then on this slide, I'm pointing out that as you look through these FRQ questions, you will see questions that involve you discussing maybe what's going on experimentally or why we would collect data in a certain way, or doing some error analysis. So we already looked at question A, asked us to explain the whole idea of heating to a constant mass. If you look at question C, this is an error analysis question. And again, it could be good to look back through your old labs and think through your error analysis questions, maybe talk through them with somebody. In this example is, let's say the student runs this experiment and doesn't cover their crucible very well. If you remember when we did this, the crucible was covered to prevent spattering. So if during the heating process it's uncovered and some of the solid spatters out of the crucible, what effect is that going to have? And justify your answer. So if there's a source of experimental data, you should always ask yourself what measurement is going to be impacted and how, like in what direction, right? So if we think about the solid spatters out, what's going to happen is the final mass after heating is going to be too low. Because what's going to happen is you are going to lose water and you will have lost some of the solid as well because it will spatter out of your container and no longer be included in your mass. So that number is going to be too low. And let's try and let me number these values. So if we kind of number these values, 1, 2, 3, when we calculate the mass of the water loss, what we did, remember we just did this on the previous page, is we took the value in 2 and subtracted the value number 3. If this value is too low, you're going to subtract a number that's too small. You're going to end up with an answer that's too big. So the calculated mass of water is going to end up being too high, and you will think that it's got more water in it than it actually does. So you're going to see the mass decrease, and you're going to think, oh, gee, I lost a lot of water, when in reality you're losing some water and some salt. So you're going to have too high mass water lost. Okay. Because yeah, there we go. Let's look at this 2006 question. This is a combustion analysis question.